Thanks for the invitation. It's really my pleasure to be here. I see that you stole that microstructure, so it looks very familiar. What I'll be sharing with you today is the work of a master's student who did her thesis several years ago already. And it was in collaboration with Aki Fagerang. And it was my first sort of foray in the whole rifting scene. So hopefully I can show you how our experiments can maybe help understand seismicity in rifting zones. So with that, yeah. So the motivation for this study is really the large or relatively large earthquakes that have occurred, specifically this one in 1989 in Malawi. It's magnitude 6.3 if I'm not mistaken. But the most important point here is that it was located at a depth of about 32 kilometers. And according to this modeling that Aki did, temperatures around these depths must be well in excess of 500 degrees C, which is of course a very high temperature for generating such a frictional instability. So the question that Aki had is what are actually the properties of these rocks when you get to these kind of high temperatures, and which rock type would be the most prone for earthquake nucleation under these conditions. So that was the motivation for the study. First, I will give you a bit of background of the world that I live in, which is the world of friction. And here we assume that we have a pre-existing fault, and that fault is decorated with a fine-grained gouge layer, principal slip zone, which we can simulate in our laboratory equipment. Another assumption is that the nucleation of earthquake slip occurs at a certain range of slip velocities. Note that this is really quite an unknown parameter. So typical experiments are done at microns per second velocities. I think mostly out of practical reasons, so that you actually finish an experiment within one day. But we don't really know what that slip velocity, how that translates to natural conditions. So I'll come back to that later on in the talk. Now, what we do in these type of experiments, we load our simulated fault gouge, and we impose a sliding velocity or a load point velocity on the sample. And then we instantaneously change that load point velocity. So that's schematically depicted in this diagram. In this case, we are sliding at a stable steady state level. We increase the velocity, and then we see an immediate increase in strength that then evolves to a new steady state. Now, this was already done in the 70s, and this has led to the development of a set of empirical equations, which are known as rate and state dependent friction equations. And it basically consists of two equations. There's the general equation, which says the friction is some reference level of friction, plus a direct effect characterized by this parameter A, and then an evolution effect characterized by this parameter B. And then there's this theta in there, which is known as a state variable, and that tells you how fast the friction evolves back to a new steady state value. And there are several different designer state evolution laws that you can use. These are the two most popular ones. There is the original slowness or Dietrich-Rena law, and this is the slip or Rena law. So the details are not important. You can spend a lot of time trying to figure out what the difference is between these two. For our purposes, for this talk, the only thing that's important is the response from one steady state level to the next steady state level, which is characterized by this value A minus B. Why is this important? Well, if we have a response where the sample becomes stronger with increasing sliding velocity, that means that we have to do more work to accelerate the simulated fault gouge. So that means it becomes more difficult. On the other hand, if we have a decrease in friction, so a negative value of A minus B, we can get the situation where the sample starts to accelerate, and we actually have an instability that can occur. Whether an instability occurs depends on the elasticity of the system that we're considering. So that's why in our experiments, we try to have a stiff system so that we can get stable sliding, and we can determine this value of A minus B. So negative values, we have a potential for the nucleation of earthquakes. Positive values, we have a seismic slip. Now, how do we do these experiments? For these experiments, we used this hydrothermal rotary shear apparatus here at the high pressure and temperature lab in Utrecht. It's a unique apparatus. It's the only one in the world. It is unique because we have an internal furnace, which allows us to heat up our sample to temperatures of 700 degrees. You can even reach 750, really push it. The vessel itself is filled with water, and the water is allowed to percolate the sample as well. So it's not acting as a confining pressure, it's just a fluid pressure that is always present. Then our sample is being loaded in a vertical direction by an instron loading frame, and that goes through a so-called pressure compensated piston. And this is a clever design, which means that no matter what the fluid pressure is inside, whatever force we apply on the top is going to be transmitted to the gouge layer, subtracting the contribution of the seals that are present here. And with that, we can apply normal stresses up to 300 MPa, as well as fluid pressures of up to 300 MPa. Our ring-shaped samples are 28 millimeter in outside diameter and 22 millimeter in inside diameter. We have an inner and outer ring that confine our gouge layer. They are coated with a low friction coating to lower the friction. And because it's a ring-shaped sample, in principle, we can reach infinite displacements. But typically, we don't go much further than 20, 30 millimeter of displacement, which for a gouge thickness that we use of 1 millimeter translates to a shear strain of about 10 to 20. So for this set of experiments, we used two powders from a felsic and a mafic sample that Aki collected. They are shown here on this map, M17 and M01. They are composed, the felsic sample is composed predominantly of plagioclase with about 25% muscovite. And the mafic sample is predominantly hornblende with some plagioclase and quartz as well. The conditions that we simulated, we tried to get as high as possible to really get to these 30 kilometer type depth. So we went up all the way to 700 degrees. Now let's have a look at some results. So what is shown here is the friction, which is simply defined as the shear stress divided by the effective normal stress. So we ignore any effects of cohesion. And what you see is in this experiment, we stepped the temperature from room temperature to 100 degrees and then 200 degrees. And then on top of that, we imposed velocity steps in half order of magnitude steps. So from 1 to 3 to 10 to 30 to 100 micrometers per second. And you can see at room temperature, a sort of standard response, an increase in friction, and then an evolution to a new steady state. At room temperature, it is velocity strengthening. And as we increase temperature, we start to see a different response to the changes in sliding velocity. And here we see this very noisy data here. Those are actually laboratory earthquakes, or stick slips, where our sample is so unstable that it's generating fast slips intermittently with periods of being stuck, so an interseismic period. Now we can take this data and use the rate and state equations with our favorite state evolution law, and then we can do a forward model as well as inversions to the data, and we can get reasonable fits so that we can get the individual rate and state parameters. So in this case, we have negative A minus B, and here we also have a negative A minus B, which you can already see from this sort of dying out oscillation that we observed. Now, summarizing all these, I think 10 experiments, on the left, you can see the friction as a function of temperature. We have the blue dots, which is our felsic sample at an effective normal stress of 100 MPa. We see a bit of variation, where it's a bit of strengthening up to maybe 400 degrees C, followed by some weakening down to a friction of about 0.45 at 700 degrees C. In contrast, the mafic sample is quite steady at a friction between 0.65 and 0.7. Now we summarize the velocity step data in terms of this A minus B parameter. And as a function of temperature, you get these kinds of profiles. They are both plotted on the same scale, just to see the difference between the response of the two different samples. And the most striking thing here is the really large increase in A-B for the felsic sample occurring at a temperature of 700 degrees C. And that results in an A-B value that is an order of magnitude larger than typical values that you would expect, for instance, at room temperature, where you have values of maybe 0.01. So it's strongly velocity strengthening, which is hinting towards the occurrence of ductility or crystal plastic processes starting to contribute. If we look at where A-B is negative for the felsic sample, it could be up to temperatures of 500 degrees C, depending on what kind of loading velocity we use. Whereas for the mafic sample, we find velocity weakening values all the way up to 700 degrees Celsius. So that is shown here in a slightly different plot. Here is A-B as a function of the upstep sliding velocity. It's basically the same data, and it shows that there is really quite a complex dependence of A-B on velocity and temperature. But if we focus on the higher temperatures, so 400, 500, 600 for the felsic sample, as well as 500, 600, 700 for the mafic samples, we see that in general, we have a smaller value at low sliding velocity and a higher value at high sliding velocity. Now, as I mentioned, at 700 degrees, the A-B values of the felsic sample were quite large, and that's hinted towards a non-frictional phenomenon occurring. So we did normal stress stepping experiments on the felsic sample at 600, 650, and 700 degrees C to see whether the friction or the shear stress was still linearly dependent on effective normal stress. And in fact, at 600 and 650, we get our sort of standard 0.6 coefficient of friction, whereas at 700 degrees, we see a dramatic or quite dramatic weakening with an internal friction of about 0.4. Excuse me. And this is very similar to what we have observed before and what other people have observed in other materials, such as westerly granite, quartz, and also on natural fault gouges from the Alpine fault. But typically at lower temperature, but then also at lower sliding velocity.
André, you had
sort of fits with
12 minutes now. Sorry,
yeah, I figured I was getting there. Thank you. So this fits with our idea of how deformation is being accommodated at these higher temperatures. On the left, you see the response to the velocity steps at 700 degrees for the felsic sample, this big increase in friction when we increase the sliding velocity. So we can try to quantify this by looking at the flow laws that we have for viscous mechanisms, for instance, for dislocation creep or dislocation glide. We get these kinds of fits. The stress exponent here is 23, so it's really nowhere close to any dislocation creep mechanism. But of course, we probably still have some porosity, so there's still a cataclastic flow component that is going on, and that is affecting our macroscopic measurement. Or the alternative is that there is some diffusion-assisted process which has a different stress dependence. Now, if you want to extrapolate this to nature, then obviously what we would really want is a microphysical model that can explain this kind of data. Now, such a model does exist, was developed in our lab, and also other people have developed these kind of models. And they predict a transition from something that is purely flowing plastically into a regime that's dominated by a competition between plastic flow and dilatant granular flow, and then further transitioning into velocity strengthening. But in order to use this model, we need to know what the mechanism of plastic flow is, and we have to quantify its kinetics. So for these samples, we don't really have that kind of data. So I did this very crude extrapolation where I looked at the velocity dependence as a function of sliding velocity, and it was more or less log linearly dependent. And you can extrapolate it to sort of natural rates, and it allows you to quantify how negative the A-B would be, and how much of the mafic rocks you would need in order for a fault zone that is heterogeneous to still be able to generate earthquakes. And that is what's shown in this bottom plot. If we consider relatively realistic loading velocities of 10⁻⁴, then that's micron per second. then we need about 60% of mafic material in our fault zone to be able to generate any kind of seismicity. So this model on the left-hand side would not have enough mafic material to allow for a rupture to nucleate in the mafic material and then propagate through this velocity strengthening felsic material that is surrounding the mafic material. So just to conclude from all of this, 12 minutes seems much shorter than it used to be. Anyway, our samples that are derived from felsic and mafic samples show negative A-B values at elevated temperatures. So it demonstrates that it's really important to do these kind of experiments under in situ conditions. At the highest temperature that we investigated, only the felsic samples showed signs of crystal plastic behavior. So when we consider the centroid depth of the 1989 Malawi earthquake, our results suggest that the nucleation can only occur within the mafic rocks, and they might propagate through the felsic rocks, but only when we have a large enough proportion of mafic rocks. So if you really want to push this further, we need to identify and quantify the rate controlling mechanisms around the brittle plastic transition. And for that, we also would need microstructures, which I haven't shown you any of today, mainly because I was worried I would run out of time. So I thank you for your attention. This work was published in Tectonic Physics a couple of years ago, so you can find all the details there as well. I'll be happy to take questions.
Excellent. Thank you, André. So if you have a question, just type it in the chat or just queue if you're quick. Do we have a question? Not so far. I would have one. You only showed one sample for mafic and felsic rock. How much would the spread be if you redid the exercise with different numbers of samples?
Oh, that's a good question. I would reckon that it depends a lot on the mineralogy. So this particular sample had quite a lot of feldspars. So typically in samples that have a bit more quartz, we see the transition to, or we see hints of ductility or crystal plasticity at slightly lower temperatures already. So for any kind of felsic sample, I would guess that this ductility would set in at 600, 700 degrees. So then the variability would be relatively minor. And I would also expect the same kind of temperatures at which you get this velocity weakening behavior. And this has to do with well, basically the classic temperatures at which people quote quartz going into dislocation creep and feldspar going into dislocation creep. So it'll be a competition between those two, what the actual temperature of transition would be.